This is lecture 42. This is the final lecture for the course, and we were discussing Char combustion. And here on this page you will see list of reactions which are possible for Char. So Char is written as C with a subscript of S, so that is S for solid. And that carbon can react with oxygen to give you carbon monoxide. So that's one possible reaction. That's the first one. Then carbon can also react with oxygen to give you CO2. Then there are a couple of other reactions, which is carbon with carbon dioxide and carbon also with water vapor. These reactions are also possible. Now along with these I have also written heat quantities that are involved in the reaction. So if there is a minus sign, then that means heat is evolved. Okay, so there is an exothermic reaction. Now out of the 4 reactions, the second reaction is actually important only if the temperature is less than 800 Kelvin, and the first reaction is dominant, that is C plus half O2 giving you carbon monoxide. The first reaction giving you carbon monoxide, that is really dominant if the temperature is more than 800 Kelvin. Second one is dominant if temperature is less than 800 Kelvin. So obviously the first one will be more important for us. So we are talking about the situation when we have these char particles getting burnt in a boiler, right? So obviously temperature is more than 800 Kelvin. 800 Kelvin is pretty low. In terms of degree Celsius, it's 527 degrees Celsius. Obviously that's not a very high temperature. And the other reactions, carbon with CO2 and carbon with H2O, these are typically not strong unless the temperatures are extreme and unless the oxygen concentration is very, very low. As long as oxygen is present, these 3 and 4, as long as oxygen is sufficient, 3 and 4 will typically not be very important. So keeping that in mind, we will try to write some theory for Char combustion and thereby get the Char combustion time. Remember again what we discussed in the last lecture. So typical 100 micron coal particle, a bituminous coal particle, entering a boiler, leaving the boiler nozzle, takes about 1 second for Char combustion, and in comparison drying and pyrolysis get over in 0.01 second. So those times are actually not very important. Char combustion time is much more important. So yeah.
Sir, first two reactions have negative heat.
Yeah.
And
so that means the exothermic reactions. So this here we are using negative sign to show that these are exothermic reactions.
Why it is so exothermic?
Because these are oxidation reactions. Okay. So only the first one we are bothered with, and the energy change with that is 9204.1 kilojoule per kg, kg of carbon. Okay. Now we understand something about Char. Let's recollect what we understand about Char. Char is mostly carbon. Char has a porous structure. It has a porous structure because the volatile matter has gone out of the coal particle, thereby creating more void spaces, thereby creating more pores. Coal itself has porosity, but Char is even more porous because that volatile matter has gone out. And the porosity of coal Char is about 0.7. Okay. And there is a huge amount of internal surface area also because of all these pores which have got tortuous connections between the pores and things like that. So it's not a solid matrix. So it has pores in it. And this Char, which has this porous structure, this is a physical structure, contains mostly carbon, we said, right? But remember at this stage, when you have the coal particle devoid of volatile matter, devoid of water vapor, devoid of moisture, it has carbon, but it also has mineral matter. So the mineral matter can, through some processes, give you ash. We understood that in the previous lecture. So what are we interested in now? We are interested in knowing Tc, that is the Char combustion time. We know that it is going to be high, but that's not enough. We want to know how to calculate Tc. How to calculate Tc is something which we want to know. Can we get some expression, some theory which will allow us to calculate Char combustion time. So, we will do it this way. We will take the reaction which I said is most important. So, just do this, C plus half O2 giving you CO. From this we can get the Char combustion time if we get an expression for ddt of the mass of Char. Okay. Suppose I get an expression for ddt of mass of Char, and then if we integrate this from an initial mass of the Char particle to 0 mass. Okay. 0 mass is when Char combustion is complete. So, you get an expression for ddt of mass of Char in terms of something. What something, that we will still have to see. Okay, maybe it will depend on temperature, maybe it will depend on oxygen concentration. The burning rate should depend on these things, right. So, ddt of mc equal to something, and then we integrate that from an initial mass of the Char particle to a final mass of 0. Then that should give you, in some way, give you the Char combustion time. That is the whole idea. Now, how do we write ddt of mc? ddt of mc can be written in terms of ddt of m of O2. So, this is mass of O2, and then we can write this as, based on this equation, we can write something like this. I will explain what this means. AP is a particle surface area, Kc is a reaction rate constant. Okay. Which reaction? C plus half O2. So, this is the rate of consumption of mass of oxygen. We are writing an expression for that. So, obviously, it is connected to the reaction that I have written here. Oxygen gets consumed, obviously, because this reaction takes place. So, how do we write ddt of mass of oxygen? We will write this assuming something. Now, this of course is related to the reaction rate. How do we write such expressions? We write such expressions in terms of reaction rate constant, isn't it? But this is one reaction for similar to which we have not dealt with so far. Okay, this is little different because this is a heterogeneous reaction. We have been writing reaction rate expressions for homogeneous reactions. This is a heterogeneous reaction. Again, why is it heterogeneous? Because we have carbon in the solid reacting with oxygen, which is in the gaseous phase. Somewhere in the combustion chamber, in the flame region, outside the flame region, we have oxygen, right? So, that oxygen is attacking the carbon of the Char. So, this is solid phase, gas phase. So, this is a heterogeneous reaction. For the heterogeneous reaction, we use something like this. We write the particle surface area, a reaction rate constant, into rho O2 at surface, S for surface, to the power n. Now, what is rho O2? It is the partial density of oxygen, and that is evaluated at S, that is evaluated at surface. So, the partial density of oxygen evaluated at the surface raised to some power n relates to the rate of consumption of the mass of oxygen, correct. So, what is this expression telling you? It is telling you that the rate of consumption of oxygen will depend on the particle surface area. That is understood, because that is where the oxygen can attack the carbon. So, it needs the surface area. So, it should be proportional to the surface area. It should also depend on a reaction rate constant, which, as we know, should depend on temperature amongst other things, right. It should depend on temperature, and it should also, the overall consumption rate of oxygen should depend on the partial density of oxygen at the surface. That is also something which we can appreciate. If you have better oxygen concentration near the surface, you will get a higher rate of consumption of the oxygen, thereby higher rate of consumption of the Char. In fact, it just occurred to me that we have seen today that video where there is this wood particle which is in air atmosphere and the wood particle in oxygen atmosphere, and the oxygen atmosphere results in the particle getting consumed very quickly. In fact, 16.02 seconds is what we saw, and in the air atmosphere it was getting consumed in 85 seconds, isn't it? So it depends on the oxygen concentration that you have. The rate at which the consumption takes place will definitely depend on the oxygen concentration. So this is fine. Remember from what you had learned previously that this rho O2 is a partial density of oxygen. Okay, so when you write just rho, it is the density of the mixture, density of the gas phase, right? But when you write rho O2, then you are talking about the partial density of oxygen. Okay, and that is evaluated at surface. So we write that at rho O2s, and we do not know exactly what kind of dependence on rho O2 this quantity will have. So we write to the power n, some number n. Okay. Now there's one problem. We haven't taken care of the sign. So what is the sign problem here? ddt of MO2 must be negative. So we include a negative sign here. So this is a global reaction of order n. And how do we write ddt of mass of char? We write this as 12 by 16 times okay, where do I get this 12 and 16? Yeah, so this is 12, okay, and this is 16. Oxygen is 32 divided by 2, so that is 16, 12 and 16. So if this is 1, this is 12 by 16. So that's why when this is MO2, this is 12 by 16 MO2. That's the logic. So we got this. So this is ddt of MC.
Power n is with the
Power, no, yeah, I got it wrong. This is n here. Yeah. Obviously, it has to be on the partial density of oxygen only. AP is the external particle surface area. AP is external particle surface area, and Kc is kinetic rate constant. The next question is, what do we do? How do we calculate Tc? This is what I was talking about, that if we get an expression for ddt of mass of carbon, then from that we can find out the total char combustion time by integrating from an initial mass to a zero mass. I'm just writing the same expression again. This is pi d squared. Okay, so what is Kc? Kc will have to have a pre-exponential factor and then an energy factor which depends on the activation energy. Okay. Let's think about how this equation can be integrated. and what are the possible problems in doing this. How do we integrate this? So one thing is that we have to get rho O2S. That is one issue. We don't know anything about this now, and when we integrate this, we'll probably have to say something about how the diameter changes, isn't it? It will go from an initial mass to a zero mass, but how will the diameter change? That also will come into picture. So first is how do we talk about rho O2S? Okay. We'll again try to simplify. This is a bit of a cheating, but we'll do that. Assume n equal to 1 again for simplicity. It's not equal to 1, but for the sake of simplicity. And in that case, let's say we have this Char particle. Again, it's not really spherical, but let's say there is some shape, and then we will say that the oxygen from surroundings will go towards the surface and get consumed there. Right? Why will the oxygen move from here to here? Because the concentrations are not the same, isn't it? So there is some little distance away from the particle, there is some oxygen concentration. At the surface, what will be the oxygen concentration? 0 or very, very low, because oxygen will get consumed there. Why? Because you have carbon plus half oxygen giving you carbon monoxide. Okay. So we have here a sink of oxygen, and the oxygen source is here, so oxygen will come this way and it will come here and it will get consumed. The rate at which it moves towards the surface and the rate at which it gets consumed at the surface because of chemical reactions, these two can be equated. All right. So we are saying that the supply of oxygen to the surface and the consumption of oxygen to the surface can be made equal, and from that we can get rho O2S. So let's see whether you agree with this. We will write all right. So what's the left hand side? What is the left hand side? Let's think about this first. Did we see AP Kc rho O2S sometime back? So it's ddt of mass of oxygen, isn't it? Actually, the negative of that, right? We saw that when? We saw that just a few minutes back. We saw that here, isn't it? Same thing, but now we are setting n equal to 1 because we are simplifying. So this has to do with ddt of mass of oxygen. So this is the consumption of oxygen, consumption of mass of oxygen because of the chemical reaction. Okay, how do you know that this is because of the chemical reaction? Because you see Kc there. You have Kc. And what about this? Here you have something new coming up. This Hm is a, anybody would like to guess? Mass transfer coefficient. Yes, so that's correct. This is the mass transfer coefficient. So, H into A into delta rho. What is this delta rho? This is rho O2 at infinity, that is far from the Char particle, and this is rho O2 as S, which is at the surface. So, Hm into A into delta rho is the rate of consumption of oxygen. Rate of, actually not consumption, yeah, it is the rate of transfer of oxygen. Consumption is here, consumption is to the reaction term. So, this is the rate of transfer of oxygen from infinity to the surface. All right, is this difficult? Should not be, because this is similar to heat transfer. Heat transfer is HA delta T, mass transfer is HMA into delta rho, right. In mass transfer, of course, sometimes we change the concentrations, we write concentrations in different ways. So, it can be sometimes it can be just concentration, sometimes it can be mass fraction, sometimes it can be mole fractions. In this case, we are using partial density. Okay. So, the difference in partial density multiplied by Hm into area, that is the mass flux of oxygen from infinity coming to the Char surface. Okay. So, this takes care of the physical transport by convection. This is by convection, isn't it? So, that is equal to the rate at which it gets consumed. Supply equal to consumption. That is all we are doing. Why are we doing all this? Because we want an expression for rho O2s. Okay. What is our objective? Objective again is to understand the right hand side better, so that we can integrate ddt of mc. Now, rho O2s will come from here. This just from here. Now, why are we trying to replace rho O2s? Because rho O2 infinity is easier to understand. What happens exactly at the Char surface? That is not very clear. Yeah. So, did we do that before? What was that? Try to recollect. What did we do? dmc dt, coming back to dmc dt. We had this. Now, rho O2s is Hm divided by Kc plus Hm into rho O2 infinity. Okay. So, we see this thing here, and this can be given a name. This can be called a Ke, which is an equivalent, which is an effective rate constant. So, Ke is an effective rate constant. What are the units of Kc and Hm? Let us see. Going back here, this is actually dmO2 dt. Right? What is the unit of partial density? Same as density, kg per meter cube. So, we multiplied the density by a non-dimensional thing to get the partial density. So, which one is that? Do you remember now? Yeah, so that we have, but I just wanted to go back to the units. What's the unit of HM? What is the unit of ddt of MO2? Kilogram per second. So, this whole thing is also kilogram per second, and area is meter squared, partial density is kg per meter cubed, and HM will be then meter per second. HM is like meter per second. What about Kc? Same. Kc will also be like meter per second, because this is meter square and this is kg per meter cube. All right, now coming back to this, Tmc dt is minus 12 by 16 AP Ke rho O2 infinity. And I think what we will do is we will not write this within bracket infinity thing, we will remove that. So, this rho O2 is just the density, partial density of oxygen a little distance away from the particle, not exactly at the particle surface. At the particle surface it can be lower, isn't it? So, Ke has the same unit of, K is an effective rate constant, it has the same unit of either Kc or Hm, right? And what can we say about Ke? Ke is approximately equal to Hm if Kc is much greater than Hm. Is this correct? If you look at this, is this correct? So, what does it say? It says that if Kc is much greater than Hm, then I mean, don't you think that if Kc is much greater than Hm, then Ke should be equal to Kc, the bigger one? No, it will not happen that way because the way they are combined. Fine. So, physically what does it mean? It means that if Kc is much greater than Hm, then the rate at which the oxygen gets consumed at the surface is very high compared to the rate at which oxygen gets transported from far field to the Char particle surface. Okay. So, we are talking about a very fast process and a relatively slow process. Which one is a faster process? So, this is a particle, the reaction that is taking place there, that is very fast. Which one is slower? The fact that oxygen has to come from the surroundings and come here and react, that process is slower. The physical process of transport of oxygen is slower. The chemical process of consumption of oxygen is fast. So, which one will dictate the overall rate? Hm. The slower process will dictate the overall thing, because okay, this can be fast, but if this is slow, then the overall process will be dictated more by this, because it can consume fast here, but if this supply is slow, then the whole thing gets slowed down. That is the whole idea. So, this is like a bottleneck. And similarly, the other condition that we have, K is approximately equal to Kc if Kc is much less than Hm, that is Hm is much greater than Kc. Hm is much greater than Kc means, again this is a particle. Now this flux is very, very efficient, it moves very quickly. Okay. So the flow situation is such that Hm is high, it comes here quickly. But if the consumption rate here is slow, consumption rate because of chemical reaction, isn't it? Because of the C plus half O2 reaction. If this is slow, then overall it will be dictated by the slower reaction thing. So this is the situation. So ultimately we understand that our dmc dt is actually minus 12 by 16 AP KE rho O2. This is something which we have to work with. We understand that if Hm is much greater than Kc, for example, then Ke equal to Kc. Okay. Now let's think about how we will integrate this. What are the complications? What is MC? MC is some rho c into pi d cubed by 6. Okay, volume into density. So that's on the left hand side. This is for the left hand side. Right hand side, do we have a diameter? Yeah, AP is actually pi d squared, isn't it? AP is pi d squared, so we have a diameter. So one possibility is that we assume, one assumption that people make is that they say that this is a constant diameter burnout. Constant diameter burnout. So they say that okay, this is diameter, it has got diameter on the left hand side, diameter on the right hand side, but they allow the density to vary. Okay, and then integrate this equation. So this will give you a Char burning time of so this is a particle of fixed diameter which somehow is burning from an initial density, initial mass to 0 mass. So density is changing, but the diameter is not changing. Okay, so sounds a little strange, isn't it? But it's actually easy to integrate this one. It's easy to integrate this one because on the right hand side you have pi d squared, so that d is constant. On the left hand side you have this d cube which is also a constant. What about Ke? Ke is Kc Hm divided by Kc plus Hm we said. How do we get Hm? That's another question. Hm can be obtained from mass transfer correlations. How do you get H? H is heat transfer coefficient, isn't it? Suppose there's a sphere like this Char particle for which you have to determine some heat transfer quantity. What will you depend on? You will depend on a Nusselt number relation. Nusselt number in terms of Reynolds number and Prandtl number. So you'll use that, and thereby calculate from Nusselt number you will calculate H. So the equivalent of Nusselt number for mass transfer is which number? There can be a okay. Number starts with S. Not Stanton number. Is it SC? Schmidt. Is it Schmidt number? No. Is it this? Sherwood number. Okay. Schmidt number is similar to the Prandtl number. Okay. And what was Prandtl number? Nu by alpha, right? So nu by d is Schmidt number. But there's a Sherwood number which is similar to Nusselt number. Okay. So Sherwood number will be h times diameter times diffusivity. So from that you can get a Sherwood number. So there are Sherwood number relations which will give you hm. Now this hm calculation, in fact, I don't think I have a relation with me right now, but yeah, for flow situation there are Sherwood number expressions which depends on Reynolds number. So I don't have that, but I'll just tell you one small thing, that if the flow is small, low flow, then the Sherwood number situation is like this. This is roughly equal to 2. Okay. If you have flow, if there is significant flow, then there will be additional term which will have a Reynolds number and a Schmidt number. Okay. Flow past a sphere, if you do heat transfer calculations, then the Nusselt number is like 2. Okay. So this is Sherwood number becoming 2 for low flow situation. So what does it tell you? It tells you that hm depends on d. hm depends on d. But if you keep the diameter constant, then d is not changing. So hm will be just one number. In that case, Kc into hm divided by Kc plus hm will be fixed number. So this is constant. Particle surface area pi d square is also constant because diameter is constant. Rho O2 is rho O2 infinity, which is again a number. So the right hand side is constant. Okay. On the left hand side, you can vary density of the Char from some initial density rho Ci to a final density of 0. Then you will get this as the Char combustion time. Okay.
For which range of diameters? The assumption that we made is true.
Okay, that's a good question. The question is for which range of diameters we can take this to be a constant diameter burnout. See, constant diameter burnout, if you think about it, it looks odd, because if it is burning, how can the diameter remain the same? But it's not so bad. In the limit, it's not such a bad idea, because the porosity can increase for a given outer diameter as it keeps getting burnt. And then finally at the last moment it collapses and then the diameter is all gone. Okay. Now we are just making the assumption that the diameter is constant. That's all. That it will remain, it will keep its integrity, and it will become more and more porous. So the density, as it becomes more and more porous, the density actually keeps coming down. So from some initial density of rho Ci, it will go to 0 density. That's the assumption that we are making. But I wrote part A here, which is a constant diameter burnout. So there is a part B, which is actually a constant density burnout. So that's the other assumption. So we don't really say that the diameter will be constant. We cannot also say that the diameter will be constant, the density will be constant. But we're trying both to find some expressions for the burning time, Tc. So the other one that we are making is, we can say that maybe there is a constant density burnout. If you take a constant density burnout, then you mean that the diameter will change. Okay, the diameter will change. And if the diameter changes, then there are again two possibilities. One is there can be a diffusion control regime which is Kc much greater than Hm. This is for high temperature and large particles. So, we are not doing constant diameter burnout, we are now doing constant density burnout. So, diameter is changing. So, if you want to integrate this, ultimately we integrate this to get the burning time, all right. We are integrating this. When you try to integrate this, you will notice on the right hand side diameter is changing. So, that is one issue to take care of. The other thing is that in Ke you have Kc and Hm, and the only estimate of Hm that we saw is for low flow when Hm is given by this. So, Hm is dependent on the diameter. Okay. Hm is dependent on the diameter. AP has diameter, Ke has Hm in it. Hm is dependent on the diameter. Fine. So, when you integrate this, it becomes a little complicated. So, one possibility is that if Kc is much greater than Hm, suppose Kc is much greater than Hm, then Ke becomes equal to which one? Hm. Okay. Always the slower one. Ke is the effective rate constant. Ke is equal to Hm if Kc is much greater than Hm, correct? Okay. So, if that is the case, then here you can write Ke equal to Hm, Ke equal to Hm, and for Hm we can use this. All right, let me repeat this. We have this expression d dt of mc equal to minus 12 by 16 ap into K into rho O2. This does not assume constant diameter, does not assume constant density. This we got before making such assumptions. Okay, correct? Now we are making some assumptions. First we made a constant diameter assumption, and then we got a burning time Tc. Forget that one now. Now we are making another assumption. We are saying that, okay, I do not believe that the diameter will remain constant. I do not believe that the diameter will remain constant. Let us try something else. Constant density. If we do constant density, diameter has to change. Okay? Because mass is density into volume which has diameter. So, if you say constant density, diameter of course will change. So, the left hand side has varying diameter. In the right hand side, let us see which all terms have diameter. AP of course has diameter, but the tricky thing is that Ke has Hm, and Hm also has diameter based on this. Okay. So, we can integrate for simpler situations. Okay, not for all cases, but we can integrate for simpler situations within constant density thing. What are the simplest situations? One is that maybe Kc is much greater than Hm. Maybe. If it is, then Ke can be replaced by Kc. Sorry, Hm, Ke can be replaced by Hm, and Hm can be replaced in terms of diameter, then you can integrate. Okay. If you do that, then the burning time turns out to be this, if you do that. So, this is for diffusion control. Diffusion control means Kc much greater than Hm. Okay. So, this is another estimate of the burning time. So, if you have a diameter, if you know the density, you can calculate the burning Char combustion time. How is this useful? Because if you are a boiler designer, you would like to know for the particular coal that you have, the chart that you have, what sort of Char combustion time you are going to get. Okay, so this is good. But we have not fully understood this, because I said that if Kc is much greater than Hm, only then we get this. This is easy to calculate, right? So, you can calculate the Char combustion time, but what I am saying is that this we still do not understand when Kc is much greater than Hm. And I just said that this is for high temperature and large particle. High temperature, large particles. So, why high temperature and large particles will satisfy this?
High temperature means chemistry will fast.
Yes. So, Kc is high and large particles. Yeah, large particles means Hm will be smaller by virtue of this expression. Okay, large particles Hm is small. Fine. So, this is what is satisfied. So, this is called diffusion control. It is actually very important. In chemical engineering, it comes up this diffusion control and kinetic control. These things come up more frequently in chemical engineering, I think. But for us also it is important. If this Char particle is moving through a zone where the temperature is high, we are more likely to get diffusion control. If the particle is large, you are more likely to get diffusion control. Okay. Then is there some other control? The other extreme. Okay. Of course, there is another extreme. What is that extreme? Yeah, so Hm is much greater than Kc. So, then Ke is equal to Kc. Right. So, we can also do that, and for that, so that is kinetic control. For kinetic control, we have Tc so kinetic control means Hm much greater than Kc. Slow chemistry. So, slow chemistry will mean low temperature. Okay. So, in the boiler zone, somewhere the particle is moving through a lower temperature zone. So, it will be more kinetic controlled. If it is passing through a high temperature zone, then it can be diffusion control. So, low temperature and small particles. All right. So, these are good expressions. You can you can calculate. If you have Kc information, you can actually calculate Tc. So, you have to know something about the reactivity of the Char. Somebody has to give you Kc equal to what? Kc equal to some pre-exponential factor into an energy factor. It's exponential minus E over R bar T. So, somebody has to give you that. If that information is available, if the particle diameter is available, density is available, then you can calculate the Char combustion time. Okay. So, we considered various limits. Constant diameter is one possibility, and if we are not satisfied with constant diameter, we can take either kinetic control and diffusion control. These will give us some limits.
Is there any range of temperature or diameter for which these two can?
Yeah. So his question is, what is high temperature and what is large particles? These things are not very clear. And then low temperature and small particles. So this sort of information people have generated by experimentation. The answers depend on the quality of coal and things like that. Okay. And these are available, but since we ran out of time, I think summarizing that will also not be possible. But this information is available. Right. So we'll close here. And if you have any question, I wanted to summarize the course, but I think there's no time, and you have another class coming up. Okay. So we did what? We did combustion thermodynamics first, chemical thermodynamics. We did chemical kinetics. We looked at some complicated chemical mechanisms like hydrogen oxygen, something about hydrocarbon oxidation, so that mechanism also, plus NOx mechanism, CO mechanism. Then we looked at some reactors, constant volume reactor, constant pressure reactor, well-starred reactor. After that, we went to detonation and deflagration. We didn't spend much time on detonation. We understood some elementary stuff about detonation, that okay, there is a shock wave on which a reaction zone rides. So shock wave supplies that energy, raises the temperature, that helps the reaction zone, things like that. And then we spent quite a bit of time on premixed flames, and then maybe a little less time on laminar jet diffusion flame. But we also did another diffusion flame, which is droplet combustion. And then finally, we have closed with diffusion flame also, because this combustion of solids is also diffusion. All right, so that's a 1-minute summary for the course. I mean, if you have any other question, we have another 1 or 2 minutes. Let me know. Yeah, we did turbulent premixed flames also. Turbulent non-premixed flames we practically couldn't do. Okay. Fine, we'll close. All right, thank you. Thank you for your patience.